write down the formula for approximating the integral from 0 to 1 of square root of 1 minus x squared dx as a Riemann sum, dividing the interval 0, 1 into n equal subintervals and using the right endpoint. So integral, this one, say 0 to 1 of something, let's say f of x dx. This is the area under this curve. In this case, we have f of x is square root 1 minus x squared. One minus x squared, square root of that always greater than equal to 0. So you imagine that in general, say f of x is something like this. Then the integral from 0 to 1, say 0 here and 1 here. The curve f of x is the black one, or this is f of x, for example, in general, 0 and 1. Integral of f of x dx is area under this curve. So that is the interpretation of definite integral. But in our case, the curve is much nicer than that. In our case, we have f of x, say y equal to f of x equal to square root 1 minus x squared. And this one is greater than equal to 0, square root of something greater than equal to 0. Now I square both sides, I have y squared equal to 1 minus x squared. This is equivalent to x squared plus y squared equal to 1. And we only work with y greater than equal to 0. And x squared need to be less than equal to 1, so that this is well defined. Now equivalently, x between minus 1 and 1. So you see that this one is the equation of the circle. But for integral, you only need to consider x between 0 and 1. In our case, x between 0 and 1, because the integral asks us to compute from 0 to 1. And y bigger than equal to 0. So it is a quarter of a circle. So if the full circle is like this, here is a full circle. 0 here, 1 here. Y bigger than equal to 0, so y is for this one, y from 0 to 1. Bigger than equal to 0. X from 0 to 1. So we always look at this region. We need to compute the area under this curve. Integral from 0 to 1 square root 1 minus x squared dx. The rest curve here, y equal to square root 1 minus x squared. X between 0 and 1, and y bigger than equal to 0. And with the setup, you know you can compute this easily using the formula of a circle. In this question, they ask us two things. The first thing is write the Riemann sum. In the second thing, compute the integral. The second part is easier. I do it now. Integral from 0 to 1, square root 1 minus x squared dx is an area, actually 1 divided by 4 the area of the full circle. And recall that for a circle of radius r, then the area is pi times r squared. In our case, 1 over 4 pi radius squared. 1 over 4 pi times 1 squared. 1 over 4 pi. The area we're working with is pi over 4, so integral 0, 1 square root 1 minus x squared dx pi divided by 4. This is the answer for question B. Now we do question A. Write down the Riemann sum. You think about the general case. For example, if I have this general case, to make it so general, I can change it from A to B. Here's a curve y equal to f of x. Integral from A to B f of x dx is the area under this curve, under y equal to f of x. And we can write down as the limit of the sum of the rectangle. If we cut this region into small thin rectangle, and we take the summation of each rectangle, limit of the summation of area of each rectangle. So the curve look like this. When the width here is small enough, you can pretend that this is a rectangle. Delta x is the width of the rectangle. And say we cut it into n pieces, so n rectangle, and let n tend to infinity. The width delta x, width of each rectangle, is the width here is delta x is b minus a over n, because we have n of them. The area of each rectangle is the width times the height, delta x times f of x. Area of one rectangle is delta x multiplies f of x. And with that, this one is limit n tend to infinity, summation f of x delta x tend to 0. This is the same thing as delta x tend to 0. And in the integration notation, we have integral from a to b f of x dx. So we are trying to write down this Riemann sum for the question. That's enough for the review. Now we write down for this case. Dividing this region into thin rectangle. So we can cut it into n rectangle. And we choose x0 to be 0, x0, x1, x2, xk, and here's xn equal to 1. We have n segments like this, n pieces. So a partition of 0, 1, n segment. h of width delta x delta x is 1 minus 0 divided by n, 1 over n. Now we have the width of the rectangle. We compute the height of the rectangle. We highlight on rectangle here. X case is here. This one, the distance here is f of xk. Height of a rectangle, height of this rectangle equal to f of xk. So area of one rectangle equal to width times height equal to 1 over n times f of xk. Now we compute xk and f of xk. So you see that x1 is actually 1 over n. x1 is 1 over n. x2, 2 over n. 1 over n plus 1 over n. x3 plus another 1 over n, and so on. xk, k over n. So in general, it is delta x times k. Delta x equal to 1 over n times k. So xk is k over n. Then this height f of k over n. F of k over n, height f of k over n by definition of the function f of x is square root 1 minus x squared, and with that f xk or k over n is f of xk f of k over n equal to square root 1 minus k over n squared. So I put it here, area of one rectangle will then be 1 over n multiply square root 1 minus k squared divided by n squared. And therefore, the integral from 0 to 1 of square root 1 minus x squared dx can be written as the limit of the Riemann sum. So, limit n tends to infinity here. Summation of the area of all the rectangle. Summation. So we have k from 1 to n. N rectangles. Each rectangle of area given by this. So this one is the limit of the Riemann sum that we want to write down the formula. Integral from 0 to 1 square root 1 minus x squared dx is the limit of this summation. And this is the answer for question A. And again, by question B, we know that this is pi divided by 4.